it's hard to get everything in focus for your high-speed shot. So it's important to have a good depth of field. Now, depth of field is a function of f-stop and also focal length. So in these three images, they're all with the same field of view, all at the same distance. The upper left-hand corner, we're using a camera with a 20 micron pixel with a 100 millimeter lens at f2. In the lower right, where we have much better depth of field, we have a camera with a 5 micron pixel. We're using a 25 millimeter lens, also at f2, and you can see we get a much better depth of field. So the obvious answer to this is that for the image on the left, we're going to have to stop the lens down considerably. And here we've done just that. We've stopped it down from an f2 to an f8. That's 4 f-stops. That's 16 times less light. So we've increased the exposure 16 times. So we've gone from 100 microseconds to 1600 microseconds. We've had to adjust the frame rate as well to 500. And of course, we don't get what we want. We don't get the high-speed shot we need. This is the depth of field tab from the camera calculator. Now remember, the black cells are the ones that we're going to enter data into. So there are two parts to this calculator. There's the top part that is just restricted to values for TS5 and IL5. The bottom section is a comparison. So this gives you the values of, well, for example, here's a TS5 with 4 times binning. We could also have values for TS3 or high spec 1 or 2, high spec 4 or 5. But let's go back here, back to the TS5 IL5 with 4 times binning, because that has the pixel size of 20 microns. So basically what's happening is, because we're using 4 times binning or 4 times subsampling, we're binning together 16 pixels, or 4 pixels wide, 4 pixels tall, to make 1 pixel. So it's the equivalent of using a much larger pixel, a 20 micron pixel instead of a 5 micron pixel, which is what those images you saw represent. So let's go back up here. We've selected an f-stop of 2, focal length of 25 millimeters. Remember, that was the image in the lower right. And the distance is 4 feet. Now down here, notice that we have the f-stop of 8, 100 millimeters at 4 feet. So again, we're set up at 4 feet, and we're using the lens that'll give us the same field of view. So with a larger pixel, we need a longer lens, and these are going to be proportional. So if this pixel is 4 times as big, the 20 is 4 times as big as the 5, and by big I mean across, that means we need 4 times the focal length. So we've gone from 25 to 100 to get the same field of view, and then we've gone from an f2 to an f8, which is 4 f-stops different in order to get the same depth of field. And of course, this calculator shows us that. If we look at the depth of field line here, it's telling us we're getting a depth of field of about 0.3 feet, which is a little less than 4 inches. And we look down here, total depth of field, just a little bit less than that, but very close. Again, a little less than 4 inches. So we've had to go up 4 f-stops. And of course, 4 f-stops is a lot less light. Let's look at the f-stop page so we get an idea of how much less light that is. These are the common f-stops. F-stop of 1, 1.4, 2, 2.8, 4. These are full f-stops. This is the relative transmittance. In other words, how much light is going to get through. So you can see that with a f-stop of 1, you get 100% of the light. You get a 1-to-1 value of the light in front of the lens and the light appearing on the image. With a 1.4, you get half as much light. With f2, you get a quarter as much light. And you see these all decrease by half as you go down. So if we go from f2 to f2.8, we've reduced the amount of light by half, going from a quarter to an eighth. If we go from f2 to f8, that's 1, 2, 3, 4 f-stops. So that's half as much light, a quarter as much light, an eighth as much light, 1/16 as much light. So if we go from f2 to f8, the transmitted light from the front of the lens to the image is 1/16 as much as it would at f2. So we'll go back to our depth of field calculator. So we can see if we're using a camera with a 20 micron pixel or a TS5 with 4 times binning, which uses the same area as a 20 micron pixel, we have to use a 100 millimeter lens, and the 100 millimeter lens, at 4 feet to get the same field of view as we got up here with a 5 micron pixel, it's going to take 16 times as much light. Or this camera would have to be 16 times as sensitive in order to get the same depth of field at the same distance and the same exposure. Okay, so now if we go back to that original 3-image shot, we have a better understanding of what's going on between the upper left and the lower right. It's the difference between 20 microns and a 5 micron pixel. Here's another example, both cameras at the same distance, actually with the same lens at f2.0. We used a zoom lens, so the image on the right was at 25 millimeters. The one at the left was at 70 something millimeters. And of course you see that you get a lot better depth of field on the image in the right. Note also that they're both 64 microsecond shutter, and the image on the left was at 506 frames a second, which is the maximum for the high spec one at that resolution. And of course the image on the right was at 991, which is the maximum for the IL5 at that resolution. So you can see that although the image on the left is slightly brighter, that camera is a little bit more sensitive. It didn't help, right? The problem is that it just doesn't get the same depth of field, and in order to get the same depth of field, we would have had to stop down the lens to about a f5.6 or 3 f-stops, and we'd have to lengthen the exposure considerably to do that.